like that. In fact, I'm going to delete that entire scene. Like that. All right. So we are live. Here we go. Let's do this. Yeah. That looks good. We're so rude, Freezer Assassin. Keep it classy. Keep it classy. We're out here at the Intrepid Sea and Space Museum right now. And you should keep a civil tongue in your mouth, sir. C-Cup is a gentleman and a scholar for being here with us this evening. He has come out here. He lives in New York City. I've traveled up from New York City. We are out here at bequest of the Intrepid Sea and Space Museum so that we can share this talk with y'all. And this is going to be a talk by a scientist from NASA Goddard, the NASA Goddard Space Flight Center. He has come up here to share his experience, with his family experience and his own experience, working on various NASA lunar exploration missions. And it goes all the way back to his family, which worked on some of the original lunar exploration. And now he's still involved with it. He's actually on the Lunar Reconnaissance Orbiter mission right now. So we're standing by. He should be on the stage in just about 10 minutes. I am probably going to see if I can't turn that background music off, because I can't do much about it. Am I still going to TwitchCon? I am going to TwitchCon, Van Roden. I am, in fact, going to TwitchCon. I will be at TwitchCon tomorrow. So I am in New York City tonight. Again, big thanks to the Intrepid Sea and Space Museum for bringing me out here so that we could do this broadcast and share this content with y'all. And then tomorrow morning, I roll out ridiculously early out of Newark, and I'm flying Newark to L.A. New York to L.A. because I play video games or something for a living. This is not anything that I ever figured that I would be saying. But y'all, video good, audio good. See the jumping around, the kid jumping around in the front of the camera there. Is everything good before Mr. Noah Petro comes on to do his talk about lunar exploration? Just give me some information in chat that everything's good to go. The question is, you're going to see another space shuttle while out there. Am I going to see another space shuttle while... Wait. Do we have enough slack on the cables? Did I leave enough slack? Let me make sure I have left enough slack on the camera cable there. Oh, there's C-Cuff. That's a Soyuz. Can I get the shuttle? That's a TV. Those are shuttle gear back there. Look here, it's right up above us right now. There's the tail. That's actually the tail of the space shuttle. Back up behind us. Here, can I get... Yeah, there you can see the heat tiles. We're sitting underneath the Enterprise right now. There you can see the wing. We're literally... There's a landing gear back there. But we're literally underneath the Enterprise. The Enterprise, of course, being one of the major attractions here at the Intrepid Sea and Space Museum. Let's lock that back in again. That looks good. That looks good. Yeah, the Enterprise is above us and the Soyuz is behind us. Exactly. We are surrounded by space hardware right now. Shuttle. Yeah, exactly. Hour from TwitchCon. LA is about an hour from me. LA is about an hour from me? Oh, it's about an hour from TwitchCon. Oh, no, I know Tanaran. Yeah. You mean when I'm going in the morning. I see what you're saying. Anyways, y'all, we are again standing by. We are live on location. We're down here at the Intrepid Sea and Space Museum. We're standing by for a talk with NASA Goddard scientist Noah Petro. He's come out here to tell about his experiences in lunar exploration. He is one of the... But, you know, I don't actually know how to introduce him in terms of the LRR, the Lunar Reconnaissance Orbiter. He should introduce himself, is the way that it should go. Can I get a couple checks, y'all? Can I get a couple checks on whether or not the upload is good? Like, are the frames good? I know we're not showing a lot of video right now, but are the... like, if you do a right-click and you look at the video stats, is everything looking good to y'all? I would appreciate it. Again, just before the talk goes... That other camera, look, the other camera's still on. That's annoying. That other camera's going to slow it down. We need to kill that other camera. Look at all the hosts from the flagship as well. Now, the rest of the flagships actually out at TwitchCon, there's a little bit of a talk that happened earlier. I know, actually, Bad News Baron was on the talk with Scott Manley and DJ Knight. It was like the resurgence of space games. I was supposed to be out there. 4,030. Thanks, Defiant. Appreciate it. And I wanted to come out here, and I didn't want to miss this talk. If you remember, earlier this year, I tried to come out to the Intrepid, and we tried to broadcast the talk about James Webb. James Webb Space Telescope. And I did not make it because the flight was delayed. The flight was canceled. The flight was like completely messed up. Hey, thank you. There you go, Deputy Project Scientist for LRO NASA. Thanks, Mutter. So I missed that earlier this year. And I really have been wanting to come out and see if we could make one of these talks so that we could do the broadcast and share it with y'all. And it was really frustrating for me. Like I was on the flight, or not on the flight, but I was waiting for the flight, then the flight was canceled, and then I drove to another airport. I tried to get on another flight, and nothing happened. Like I just couldn't get out here for that James Webb Space Telescope shot. Luckily, Seacuff lives here, and the subways are running, which I think is a thing that usually happens in New York City. And so he made it over from where he lives here in New York, and actually did the James Webb broadcast from his phone, which he had never done a broadcast before. Much less from just your phone, much less from anything else. Hey, Mink Sauce, how's it going? And Bob the Everlitting. Sound seems a tiny bit peaky. I've got it trying to, it's just my microphone right now. We are going to be piped into their microphones at some point, so we don't, we'll be using different microphones. This is not the microphone we're going to be using. Flight cancellations are the worst. Got stuck in an airport for a few hours before the last Intrepid stream. Oh, man. Didn't tell me he wasn't coming until I was already at the Intrepid. We're good to go, and you're on camera right now. Hi. Yes, hello. It's actually is. Thanks, museum staff member. Just random people walking in front of the cameras. No, it's fine. We are all good to go. We're actually live right now.
So the whole world.
Yeah, that was, yeah. If we don't mention it, never mind. They can hear me right now. We need to have like lasers that denote where the camera is pointing. Yeah. It's all good. It's all good. You did. It was right about your like eye level, and it was slightly lower on Siobhan. My microphone is live right now. So yes, we are good to go, and we're just doing the introduction. Y'all, we had some of our beautiful, wonderful museum staff walk over and talk to us and be like, oh, y'all ready to go? And I'm like, actually, we're going right now. So again, we're at Intrepid Sea Air and Space Museum. This is their family astronomy night, something that they do on a regular basis throughout the nicer months of the summer. And a lot of times during family astronomy night, they'll have a talk with somebody. A lot of NASA people came out this year. Like I was saying, James Webb came out earlier. Amber Strawn, I think, was the scientist that came out for James Webb. And now we've got Noah Petro from NASA Goddard talking about lunar exploration. In just a couple minutes here, afterwards, they're doing a little bit of a... Right now, we're actually might be able to check out some of the family astronomy stuff. Warning, education zone. It is an education zone. I mean, you're not wrong. It's cool because the little stage that you're seeing in the corner there, that little stage is a place that they do some science type of demonstrations throughout the course of the day at the museum. I know earlier we had to move around because they had like a vacuum. It was like living and working in space. Zoom in. There we go. That looks good. All right. And there are people walking in front. That's the active walkway there. Oh, it looks like, whoa, dude, he put on a suit. He looks super snazzy now. Yes. Hey, thanks for the resub there, Paul. I appreciate it. I don't have notifiers or anything on. Again, massive thanks. I am out here because the Intrepid Museum made it possible for me to come out. They got flights and stuff like that so we could come out here and share this broadcast for y'all. So again, massive thanks for the Intrepid Museum making it so that we can share that with y'all. Hey, Jonathan, how's it going? How are y'all doing? And again, oh, one more thing. Important thing to note here. There will be a little bit of a Q&A time at the end of the stream. And so we're actually going to take some of the questions from Twitch chat, and we'll ask them over here.
Hi, good evening. My name is Ellen Silberman. I'm the Director of Public Programs here at the Intrepid, and I'd like to welcome you to our last Family Astronomy Night of 2017. I know we have one more Astro Cafe on November 3rd, but this is the last Family Astronomy Night, and we look forward to seeing you for more of them next year. After our wonderful speaker this evening, you know, there are telescopes outside on the flight deck, and there's also a pop-up planetarium tonight in the back, so go back there and have fun. What else do I want to say? The other program I want to let you know about is on November 14th. If there are any fans of The Martian here, Andy Weir is going to be here. He's going to be here on November 14th. That's just because it's not for like kids. If you have someone who's a fan who's, let's say, 12, 13, 14, bring him, her. So he's going to be here. It will be his only New York public appearance. We're really excited. And for those of you who know anything about Andy, he hasn't been in New York before because he really had a fear of flying. But now with the success of The Martian, he realized he better get that worked out because he's going to be speaking at Houston and DC and everywhere. So it's really exciting. And it's part of a theme, I guess, because his book's about the moon. It takes place on the moon. And we have the moon in 2018. I hope we're going to be starting with a lot of our anniversaries for the Apollo missions. So there'll be a lot of great programs. I'm just curious, how many of you, if you wouldn't mind raising your hand, if this is your first astronomy night here at? A lot of people. Wow, that's great. Please do me a huge favor because I'm really important. Before you leave, go back there and for me, fill out on those iPads a survey so I know how you found out about this and why you're here, because we really do these for the audience. It's important what you want, how you hear about it, so we know how to reach you. And that's really all I have to say. I'm very thrilled to introduce our guest, Noah Petro. He's from Goddard, NASA's Space Flight Center. And I'm going to let him tell you about himself because that's part of his presentation. So I'm going to turn it over to Noah.
Great. Well, thank you so much for the lovely introduction, and thank you, everybody, for coming out, spending your Friday night here out on the deck of the Intrepid. This is probably the most unique environment I've ever had to deliver a talk, and it's really with great privilege that I'm here tonight, kind of returning home. I grew up about an hour north of here in Bedford Hills, New York. And so as a child, I'd come to the Intrepid and look in awe at the airplanes, at the artifacts, the space artifacts, and one might say that my sort of passion for space exploration was started in part because of my visits to the Intrepid as a child. Having grown up in New York State, I was very lucky to have some amazing educators, and I understand there's some teachers here tonight. Hands up if you're a teacher. Okay, well, first of all, thank you all for teaching. Let's give everybody a round of applause, teachers there. And my interest in space science really came from my parents. My father was an engineer on the Apollo program, but my interest in geology came from my high school science teacher. Steve Kluge at Fox Lane High School in Bedford was really the linchpin for getting me interested in earth science and geology, and then going on and getting interested in planetary geology. And so tonight I'm going to talk a bit about some of the work that we're doing on the moon, in studying the evolution of the moon and my perspectives on why the moon is important. And also looking back at over 45 years of lunar exploration, both robotic and with humans. It's really an honor to be here at a ship that had such important roles in the early development of the human spaceflight program, with the assistance of the recovery of both a Mercury and the first Gemini space launch, a human space launch. So that was really an important part in building the way for humans to go to the moon. And so one of the things that I'll talk a little bit about is how we got to the moon, how it was not just an overnight decision, how a lot of work and planning went into getting humans to the moon and back to the Earth. So I want to start by talking a bit about perspective. I'm going to show three different perspectives on the moon. This image here, which is hard to see, but these two small dots on the left is the Earth, on the right is the moon. This is an image taken just over a month ago by the OSIRIS-REx spacecraft as it made a close approach to the Earth on its way to the asteroid Bennu. In a year, OSIRIS-REx will rendezvous with Bennu and begin 1 year of mapping of the small body in preparation for sampling that asteroid and bringing that sample back to Earth. What I love about this picture, though, is it gives a sense of perspective of the moon as not being some distant object in the sky, but really being our celestial neighbor. In one image, you get both the Earth and the moon, the full illuminated disks of both objects. And so this sets the stage for sort of how I perceive the moon as being not some unrelated rock in space, but really as being an extension of the Earth. I consider the moon to be sort of the 8th continent of the Earth. Each of the continents on our planet tells us something very, very important about how planets work. We, as geologists, go and study all of the continents to better understand how the Earth works, but the moon provides an opportunity to understand how the Earth or Earth-like planets have worked over billions of years. The moon's surface preserves a record of the events in our corner of the solar system over 4.5 billion years. Whereas on the Earth's surface, because of our wonderful atmosphere that protects us, it also helps in recycling the surface of the planet, basically erasing that history. And so in order to peer back into the history of our solar system, the lunar surface provides us that wonderful context, that Rosetta Stone for understanding the ancient history of the solar system, as well as processes that are going on as we speak today. So when we look at the moon, and tonight's not a great night to look at the moon, it's a beautiful night to look at other objects in the sky, but over the next week and 2 weeks as the moon becomes full, I want everyone to take a moment and look at the moon and appreciate not just that it's a place that we visited with humans, we have a robotic spacecraft orbiting the moon right now, but also that the moon is this record that we as planetary scientists attempt to unravel and understand how not just the moon works, but all planets in the solar system, and indeed any solar system in our universe, operate. This is another perspective. This is an image taken by the spacecraft that I help operate, the Lunar Reconnaissance Orbiter. This was an image taken just over 2 years ago now of the Earth setting just beyond the lunar limb. You can see in the picture here that the rugged lunar surface is silhouetted against the beautiful backdrop of the full Earth. And so, as I said before, we use the moon as a sort of a cornerstone for understanding all planets in the solar system. But we always like to look back at the Earth, not just to calibrate our instruments and make them better, but also to reinforce this perspective that the Earth and the moon are a pair, cosmic siblings, if you will. And so in order to understand one, you have to understand the other. And lastly, this is the perspective that we here on the Earth get of the moon as it goes through its phases over 29 and a half days. And I include this because this is, first of all, a wonderful example of how we apply our data that we get from the Lunar Reconnaissance Orbiter. This is not actually based on images. This is based all on data from our spacecraft to recreate at hourly intervals over the course of an entire year what the moon would look like. And so as over the next month, hopefully everybody takes time to appreciate the moon and look at the changing sort of appearance of the moon, that of course the moon is not changing, it's just our interpretation, going from the rugged terminator as it sweeps across the surface, and as we get to a full moon, the very basic fundamental difference of the moon, the dark volcanic lava flows that cover portions of the near side, and the bright, heavily cratered ancient crust of the moon that are so apparent when the moon is full. And even with a full moon and even a simple pair of binoculars, you can begin to pull out some of the geologic history of the moon, the bright, fresh impact craters that have ejected material thousands of kilometers across the surface. The ancient, heavily cratered crust of the moon formed 4.5 billion years ago. And then the more recent 2 billion-year-old volcanic lava flows that have flooded portions of the near side of the moon. In essence, the moon is this treasure trove of geology. As a geologist, it's a perfect place to study processes in the solar system. You don't have water eroding the surface like a river like the Hudson here. You don't have weather, rain eroding the surface. All you have is the pure fundamental aspects of geology. And so as that stepping stone for understanding our moon, we apply that across the solar system, whether it's looking at Mars, asteroids, even the surface of Pluto that was so wonderfully revealed by the New Horizons spacecraft. All of our understandings of the planets hinge on our interpretation of the moon. And so what I'll talk a bit about tonight is how some of our interpretations of the moon have come almost full circle in 45 years and reevaluating what we thought we once knew and now know to be different because of the data we have from the Lunar Reconnaissance Orbiter. But first, I want to talk a little bit about being a geologist. Context. Context is something that I like to call a geologist's best friend. Now, geologists have actual real friends, not just vague concepts. Trust me about that. But context is what takes a rock from being a rock and makes it a specimen, makes it something special, more than just a rock sitting somewhere unknown. when we apply context, the understanding of where something came from, in this case, a boulder becomes something more important. This is a picture that I got from a Hofstra University website describing a glacial history. This boulder becomes something more important when we understand where it is. This is a boulder in Central Park. And the first question a geologist would ask is, first of all, how did that boulder get there? There's no mountains nearby for it to have rolled down, but it's sitting on this very smooth surface with scratches on it. And as we unravel the geologic history of southern New York State, and indeed of all of New England, we understand that about 10,000 years ago, glaciers covered most of New England and indeed most of North America. And so this boulder becomes a random rock sitting in the middle of Central Park to a glacial erratic, a rock deposited by that glacier 10,000 years ago. And so understanding the context of the environment of where rocks, or really any specimen, comes from is what helps geologists tell a story. Every rock is like a book. There's a story to be told. But without the context, it's a paper torn out of a chapter. You don't know where it came from. You don't know what its setting is. But with context comes a really wonderful story. And this is sort of why I became interested in geology, is that storytelling, that unraveling, that mystery. And so what I hope to do here today is talk a little bit about how we can put Apollo, and particularly Apollo 17, into context and tell a new story about our exploration of the moon. But first, let's talk about how we got to the moon, because I think it's important that we understand not just the context of the rocks that we brought back, but why we went to the moon and how we got to the moon. And so one of the real kicking off points was October 1st. We just celebrated the 60th anniversary of the launch of Sputnik. Now, looking across the audience, I don't see many people who were alive at the time of Sputnik, which is fine, but for those of you that were, this was a momentous moment, really, in human history. For the first time ever, humans put something into orbit around the Earth. And tonight, if you're outside and you get your eyes dark adapted, you'll see maybe several satellites passing overhead. Just last week, I saw the space station fly over my home in Washington, D.C. We're used to seeing things flying overhead, but now, in 1957, this was new. This was a shocking moment in human history that for the first time we could put something orbiting around the Earth where getting any place on the Earth became feasible relatively quickly. So with this moment really set in motion the space age. Now we live in the space age, we're used to it. We have 5 astronauts living on the International Space Station right now. We've been living in space continuously for over 15 years. Space is something sort of familiar to us, but at this point this was a real shock. Now fast forward only just over 4,300 days later, we were launching humans to the moon. From launching something a little larger than a grapefruit, about a bowling ball in size, to sending humans to the lunar surface, 2 humans to the lunar surface for a day, and having them come home. It's just about 12 years of time difference. So I don't know where you were 12 years ago, but we didn't have iPhones, which may or may not have been a good thing, I don't know. But you can imagine the amount of technological advancement that had to go on for 12 years to get from the simple launching of a satellite, a very simple satellite, into Earth orbit, to launching humans not only to the moon, but getting them back. And so that process of getting humans to the moon and back really started, and this is one of the only text slides I have, I apologize, but I wanted to really outline the history, because as a novice history buff, this sort of thing fascinates me. But as much as October 1st was the stepping stone, people have been thinking about getting into space, not just for years before, but for decades before. And it was the science fiction writers that really pushed the envelope of thinking, well, what could we do in space? So October 1st was the sort of kicking off point of the space age. The US responded to the Soviet launch of Sputnik with their first successful launch. There was many failed launches before, of Explorer 1 in January of 1958. Just a few months later, the Air Force funded an observatory to create a map of the near side of the moon. Now, why that is important is because even at that point, in April of 1958, it was recognized that the moon was a destination. This wasn't done just as a pastime for astronomers, but really to start bringing our understanding of the moon up to speed so that we could prepare for the eventual sending of humans to the moon. Now, there was no official program to do so. NASA hadn't even been funded or started until October of that year. but it was recognized by the Air Force, at least, that the moon was going to be a destination. 1959, April 9th, the first group, the Mercury 7 astronauts, are selected. Scott Carpenter, who is pictured right here, set foot on this very aircraft carrier on his return from Mercury Atlas 7, Aurora 7. And so at that point, that's where sort of the American imagination of what was possible in space came to be. Later that year in September, the first impact onto the moon, the first artificial impact onto the moon occurred, Lunar 2. So, we're going essentially 1 year, a little under 1 year, 2 years from the first launch into Earth orbit to actually getting something hitting the moon. And then in October, the first images of the far side of the moon come back. And I'll talk a little bit later on about what the far side looks like, but those were some stunning images that for the first time in human history revealed what the far side of the moon looked like. 1960, in January, so this is just before even NASA had announced anything about going to the moon, the name Apollo was selected. I think it was selected because it obviously represented what would have been a major milestone, a major achievement, also required very heavy lifting. And so Apollo was named as the follow-on to the Mercury program. For those of you that have been here on the Intrepid, there's a beautiful mock-up of the Mercury capsule downstairs. You can see that it's really no larger than the driver's side of a small car. And so even in 1960, it was recognized that we need a larger spacecraft, something to get humans not only into space, but more humans into space, and eventually onto the moon. Later that year, NASA decided what would be needed to get 3 humans into space. And finally, in July of that year, Apollo was named as the program that would get humans to the moon. Now, of course, at that point, we didn't have a moon program. It was not funded, but it was recognized. NASA recognized that this would be something that would be needed. And then things get really interesting in 1961. President Kennedy is obviously embroiled in incredible Cold War with the Soviet Union. And on April 12th, the first human goes into Earth orbit, Yuri Gagarin. And just as Sputnik was the beginning of the space age, Yuri Gagarin was really the beginning of the space race. Because that set in motion in very short order the president saying that the U.S. needed to do something to respond and pass the Russians, the Soviets, in space. It was recognized that space is the high ground, and we needed to get there. April 20th, the president sends a memo to his vice president and asks the simple question, is there any space program which promises dramatic results in which we could win? President Kennedy recognized that we needed to do something and we needed to win, not just for the sake of beating the Russians, but also for the sake of national pride and showing the American people that we could do it. Later that month, a week later, the president responds in a very long response saying that manned exploration of the moon, for example, is not only an achievement with great propaganda value. So immediately, they're sitting in a stage that Apollo was supposed to be for propaganda value. But it is essential as an objective whether or not we are first in its accomplishment. And we may be the first. And thus, he also states that the U.S. could probably land on the moon with humans by 1966 or 1967. A day later, Wernher von Braun, really the father of heavy space flight, sent a memo to the vice president saying, we have an excellent chance of beating the Soviets to, and he underlines this, the first landing of a crew on the moon, and then parenthetically responds, including return capability, of course, which is nice to see that they were thinking about actually returning the humans back. And then a few days later, Alan Shepard becomes the first U.S. astronaut in space. So within the span of just under a month, a lot happens. The U.S. responds, gets Alan Shepard into space. 20 days later, President Kennedy delivers one of his most famous speeches to Congress, in which he has the famous words, first, I believe this nation should commit itself of achieving the goal before this decade is out of landing a man on the moon and returning him safely to the Earth. And really, in that span of very short time, the President recognized that the moon was an achievable target and set in stone a deadline, which is always good for the government to have a deadline. Trust me. And we usually get that deadline too. And in this case we did, of getting humans to the moon and back. Doesn't say anything about science at this point, but just says that we need to do it. And thus begins the push to go to the moon. Now, by the time that decade was out, we had landed on the moon 2 times. Apollos 11 and 12 landed in 1969. Apollo 11 on July 20th became the first human landing on the lunar surface, and by that point, the U.S. had leapfrogged the Soviet capabilities in going not just into space, but into deep space. But at that point also, it became more than propaganda. Science began to force its way into Apollo. If some people had their druthers, Apollo 11 would have been the only mission to the moon. Neil Armstrong would have gotten out, picked up some rocks, planted the flag, got back in, and come back. But there was enough people who recognized the scientific value of exploration of the moon that it didn't stop at that. Indeed, we pushed further and further and further. And with each Apollo mission, increased our capability of what we could do and bring back. You'll notice, though, that in the 6 Apollo landing sites on the near side of the moon, so this side over here on the right is the side of the moon that we see from the Earth. All of the landing sites are roughly equatorial. That means they're right around the middle of the moon. And they're all on the near side and roughly clustered around the middle of the near side. We have no landing sites on the far side of the moon, and we have no landing sites near the poles of the moon. And indeed, you'll notice that there's this incredible difference between what we see on the near side and the far side. On the far side, far less volcanic activity, much more rugged, ancient highlands, ancient surface of the moon. And so this near side, far side difference, this dichotomy as we call it, is one of the long-standing mysteries of lunar science. Now, we come to think that maybe there was some difference in how the moon formed that locked in this near side, far side difference, but we just really don't know. On the far side of the moon, there's an ancient impact crater that's about the size of half the United States, the largest and oldest impact basin or crater in the inner solar system. Indeed, perhaps the largest crater in our entire solar system. And perhaps a far side mission, a sample return mission, robotic sample return mission would begin to unravel and reveal some of the mysteries of the lunar history. And again, when I say lunar history, I also mean part of that is Earth's history. One of the outcomes of the sampling from Apollo is the hypothesis that comes out that the moon was once entirely molten. You can imagine 4.5 billion years ago, if there were continents to stand on and an atmosphere to breathe on, you would have looked up at the moon and you would have been able to see this glowing red ball in space covered in molten rock. It would have been much closer. And then over millions and millions of years, the crust would have formed. And so unraveling the history of the moon was really begun from those samples from the Apollo program. Apollo 17, the last mission, which celebrates its 45th anniversary this December, was the culmination of the Mercury program, the Gemini program, and all of the Apollo missions that came before it. It was the last of what was known as the J missions. Those are the heavy-duty lunar missions. 3 days on the moon. They brought a rover, a car that they drove around on the surface, which allowed them to explore a greater amount of the area around their landing sites. There was 10 experiments that were brought to the surface of the moon, 10 experiments that were conducted in the orbiting command module as well. You can see it, well, you probably can't see it right, but at the right-hand side of the screen shows some differences in the amount of distance that the astronauts traveled, going from just under 1/4 of a kilometer from Apollo 11 to over 35 kilometers at Apollo 17. They brought 514 kilograms of experiments to the surface as opposed to only 102 at Apollo 11. Apollo 17 was outside. They were doing spacewalks on the lunar surface for over 22 hours as opposed to the 2 hours and 24 minutes Apollo 11 spent on the moon. Everything had leapfrogged our previous capabilities. And finally, Apollo 17, as a geologist, perhaps most importantly, brought back 110 kilograms of rock as opposed to the 21 kilograms that both Neil Armstrong and Buzz Aldrin collected on the lunar surface. But I should point out that that experiment package, which you can see actually was less than they brought to the moon on Apollo 16. They didn't break every single record, which I know bothers the surviving Apollo 17 astronaut to this day. There's one experiment that's not included in this chart. It was a 74.8 kilogram experiment, and I use the term loosely, that also represents the culmination of all of the development. That experiment was a trained geologist. Jack Schmitt was the first non-test pilot to go into space. He was the only scientist to go and land on the moon. And as such, I like to think of him, although I wouldn't say this to his face, as an experiment. There were some that believed that it wasn't possible for a non-test pilot to go to the moon, that you had to have, I hate to use this term, the right stuff. Ooh. to get to the moon. And Jack, through his training, became a certified pilot. There's a T-38 parked on the deck here. He learned to fly a T-38. He was a very, very good pilot. And he went through all of the training. And finally, when Apollo 17 was announced as the last mission to go to the moon, there was intense pressure from the scientific community to get a scientist to go, to get Jack Schmitt to go to the moon. And indeed, that pressure convinced Deke Slayton to swap the crews, or swap the lunar module pilots. And so Jack was put on that mission. He was originally scheduled to go to the moon on Apollo 18. Apollo 18 was canceled in part to make way for the development of the airplane that's hanging above us right now. And so Jack got to go to the moon. He was in the first group of scientist astronauts. And one of the things that made Jack, well, in many ways he's unique, not just he walked on the surface of the moon, there's only 12 people who can say that, is that he was part of the Apollo program from its really early days in preparation. From 1965 on, he was there. He assisted in the geologic training for the astronauts that got to go to the surface. He analyzed the samples. He had, and still has to this day, an encyclopedic knowledge of what happened before him. And so he was perhaps the most prepared person to go to the moon. He knew what to look for as a geologist, as a scientist, in order to maximize those 22 hours he was on the lunar surface. And indeed, he maximized the science he did in the entirety of that mission. If you recall, that first picture I showed is one in a series of pictures he took of the full disk of the Earth, the, quote, blue marble picture, one of the most heavily reproduced images NASA has ever produced. And he was taking pictures of the Earth because he was doing amateur meteorology experiment on the transit out to the moon. So he was one of the first people he was a weather satellite, basically, in the era before weather satellites. So he was giving weather forecasts. Looks like it's going to rain tomorrow in Houston. Well, it rains all the time in Houston. That wasn't a really, but he would give these reports. So he was constantly making scientific observations, whether it was of the Earth or the moon while he was in orbit around the moon, or while he was on the surface collecting the samples. So Jack was and is this great experiment showing that scientists in space are valuable and can do incredible things when allowed to go into space.
Seconds. 10, 9, 8,
Here, I'm gonna
7.
Let me pause that for a second. I want to talk about the launch of Apollo 17, but I could talk about it or I could show it. And showing it's going to be much more interesting because, quite honestly, some of it is hard to describe. There's a great documentary. I suggest everybody, it's online. It's called The Last Steps. Came out last year, and it's sort of a retelling of the mission in condensed time. I pulled out the launch portion of it. Apollo 17 was the only night launch of the Saturn V rocket, the largest rocket ever to send humans into space. I was not yet born, and so I never got to see a Saturn V launch, but I'm told they were one of the most spectacular sights to see and things to hear and things to feel. If you are impressed by a 4th of July show where you feel the reverberation of the large explosions, this would knock your socks off, literally would knock your socks off. And so I'll let the countdown and launch of Apollo 17 speak for itself.
Seconds. 10, 9, 8, 7. Ignition sequence.
Okay, so there's more to it, obviously. Yeah, it was they obviously went off into space a few hours after launch. They did another burn to go on their way to the moon. So Apollo 17 had several objectives. All of these missions were clearly laid out, almost scripted, as to what they would do. Based on the success of the Apollo 15 mission, which completed in April of 1971, mid-1971, Apollo 17 set out to both sample ancient crust as far from the Apollo 15 landing site as possible. They wanted to sample young volcanic material. All of the volcanic rocks had been brought back by the Apollo missions before that were about 3.8 billion years old. And there was a thought that where Apollo 17 would go would be young. They wanted to get increased coverage by the orbiting command module, perform geophysical measurements in an area that had layering, and so the volcanic layers were identified there, and deploy an experiment package as far east as possible. And so in February of 1972, that landing site, known as the Taurus-Littrow Valley, was selected. This is an image of the Taurus-Littrow Valley taken by the Apollo 17 mission. Right here is the command module. This is a picture taken from the lunar module before they descended to the surface. And they were aiming for a point right here in the middle of the valley. Now, just to give, again, some context for the valley, they identified five specific targets. They wanted to get this light material that was thought to be an avalanche coming off of this mountain peak here. They wanted to sample material from the avalanche, the lightly cratered surface, dark surface here, the heavily cratered surface here, from these two mountains, and from what's known as the Sculptured Hills, a third mountain system in that valley. Just to give context for the scope of the Taurus-Littrow Valley, this is the Grand Canyon. It's about just under 2 kilometers elevation change. The Taurus-Littrow Valley is a deeper canyon than the Grand Canyon and much older. And so this was an incredible technological achievement. We went from Apollo 11 not really knowing very well where they landed to pinpointing a landing spot with Apollo 12 to eventually being able to land in a valley deeper than the Grand Canyon. So within the span of just 4 years, we were able to really push the limits of what we could do with 1960s era computers. So this is an image of the Taurus-Littrow Valley taken by the spacecraft orbiting the moon today, the Lunar Reconnaissance Orbiter. Not much has changed. The only real difference, and it'll be apparent in some subsequent images, is that there are some footprints left behind and some hardware the Apollo astronauts left behind. This is a map showing the extent of where they explored. And again, by this time they had a rover, so they could explore a much greater portion of the Taurus-Littrow Valley. To put this into context, here's those EVAs on top of Manhattan. They landed the lunar module in the middle, essentially, of Central Park. And they were able to cover a great portion of, well, what would have been Manhattan, including a little trip across the Hudson River. Took them 3 days to do this, which based on traffic is about the right amount of time to do this exploration. For additional context, this is Apollo 11 placed on top of the Intrepid. You can see that Apollo 11 barely would have left the deck of the Intrepid Museum here. I should point out that these maps were produced by a colleague of mine, Brent Gary. Brent's grandfather was the commanding officer of the Intrepid in 1971 and 1972. So Brent was very happy to put this together for me. Brent's getting ready to become a dad in a week, so he's trying to get his mind off of that as much as possible, I think. So after the mission, there were several mysteries. While they had gone to each of these 5 targets, they were not sure of exactly what triggered or caused that avalanche of material. And I'll talk a little bit more of that in a minute. And finally, the Sculptured Hills, this knobby, hilly, textured terrain to the east, they weren't really sure that they sampled anything from it. They expected to be able to get boulders, big boulders that had rolled down the mountains, but hadn't seen them. And so now, after 45 years, we can place the context of exploration that those brave astronauts put into Apollo 17 into a new context with the help of the data from the Lunar Reconnaissance Orbiter. This picture at the right I include because I can't talk about Apollo 17 without showing the famous orange glass. Yes, there is color on the moon. It's not all black and white. That orange is really a radiant orange color, kind of like an emergency sign orange that was very clear to Jack when he stumbled across it, surprisingly, during Apollo 17. So let me talk a little bit about the LRO mission. We launched over 8 years ago, and we've been in orbit ever since. We just completed 100 lunar days, 100 months of mapping the moon, the longest ever mapping mission of the lunar surface. We have 7 instruments ranging from a radiation detector, an instrument that measures the temperature of the surface, to taking an instrument, the LRO camera, which has a really high power camera that can image features on the surface at the centimeter scale. The benefit of being at the moon for this long is, again, context. Understanding how the moon is changing over 8 years. Before LRO, we thought the moon was static, unchanging. Now, it's still not changing very much, but we're able to measure those changes. For instance, at right is a new impact crater that formed on the lunar surface excuse me, by taking a before and after images, we can actually detect changes on the surface of the moon. And one of the things that we were initially set out to do is create an atlas for exploration, to map the moon at a scale sufficient to identify safe landing sites for future human and robotic missions, to map the presence of volatiles at and near the surface that could be used by future explorers, and to find places that are illuminated for a significant portion of a lunar day. And so for all of these things, LRO set out to set sort of a map for future exploration. But our map of future exploration includes exploring the Apollo 17 landing site and all of the Apollo sites as well. This is a series of images taken over several months by our spacecraft under different illumination conditions, going from images early in the lunar morning when shadows are long to lunar noon when the sun is directly overhead. And at the middle, you can see the lunar module descent stage, the bottom half of the lander of the Apollo 17 mission, sitting on the surface. You can see the car, the rover that they left behind. And indeed, you can see a small smudge moving like a sundial, the flag, still flying on the surface of the moon. And this was a big surprise. No one expected the flags to still be standing. These were not heavy-duty, specially designed, NASA-strength industrial flags. These were essentially off-the-shelf polyester flags that fly in every government building in the country. When they went to the moon, they thought, well, let's not invest a lot of money in sending a flag. And indeed, the polyester is still there. We don't know if the flag still has any color to it, but if you've ever left laundry out in the sun for more than a few days, you know that things bleach pretty quickly. So indeed, we anticipate that the red, white, and blue have now turned to solid white. But that's the landing site. I'm going to skip through that video because it just goes into more detail about what we can see on the surface, including the experiments, the footprints, the backpacks that the astronauts left behind, the backpacks that my dad helped build. So when I look at these landing sites, I see a little bit of my family history on the surface as well. I'm going to explore two questions that we've been able to address. One is, what is the origin of this light mantle, this sort of avalanche material here, and where did this sculptured hills come from, and what does it represent? Because those are the two really lingering, long-standing questions that nobody has been satisfied with for 45 years. So on EVA-2, this is the second trip that the astronauts took. They drove from their lunar module, and this was the long trip south in our Manhattan view, all the way to the base of the South Massif, this mountain. And part of that was traversing over this avalanche deposit, sampling it at places, coming back, sampling that wonderful orange soil, and going back over a span of several hours. Now, as I mentioned before, Jack, being the geologist, spent almost the entire time while they're driving explaining what he's seeing. And for folks that have ever driven with me, you understand when I drive past an interesting outcrop of rock, I do a lot of describing and talking. So I can only imagine what Jack's crewmate, Gene Cernan, would have thought hearing this ongoing dialogue about block size and craters, and might have gotten a little much. But Jack was maximizing his time on the lunar surface. And really, there's no better record of what the surface is like than what Jack recorded. So during their transition to the light mantle, they sampled that material. The age of that material was determined to be about 100 million years old, that avalanche occurred about 100 million years ago. And so it was immediately recognized that this beautiful crater on the southern near side of the moon, Tycho, which has all of these rays of material, ejecta, streaming across the surface, that one of those rays looked like it was heading sort of towards the Apollo 17 landing site. And so the thought was that avalanche was triggered by ejecta from this distant crater. That crater is about the same distance as New York to Houston from Tycho to the Apollo 17 landing site. And so it was thought that material was triggered by Tycho, and so that 100-million-year-old age was the age of Tycho. This is an oblique image taken by our spacecraft, so we're sort of looking out the window. You can see that there's the avalanche here, but there's also this wrinkle that goes along the floor of the valley. That's a wrinkle ridge, a tectonic feature on the lunar surface, basically the expression of a fault on the lunar surface. And so we started looking at the relationship between that fault and the light mantle deposit. This is a perspective view using high-resolution topography that we've created of the valley. And so you can see this is if you were standing on the top of the South Massif. There's the avalanche, and there's that fault right there, known as the Lee-Lincoln Scarp. And so in looking at that, one thing sort of started coming out to us very quickly, that in looking at that light mantle deposit, and this is another view looking straight down, but this time with the sun directly overhead, and so light or color differences are very apparent. And it looks like there was a brighter or fresher looking flow of material and a darker or older flow. And immediately that started getting us thinking that maybe this wasn't a single avalanche event, but actually multiple avalanches that happened over multiple times, a couple 100 million years or tens of millions of years apart, not just a single event. And then we made the connection between this tectonic feature, this fault that runs right through the valley, and thinking, well, what's the age of that fault? And that fault comes out to be about 100 million years old as well. And so we put together those two events and said, well, maybe you don't need to have material coming all the way from the Tycho crater. Maybe you've got an avalanche caused by moonquakes. The moon is seismically active. We've known that now for almost 50 years. And so we put forward the hypothesis that instead of having material from the Tycho crater, we have essentially earthquake debris falling off of the South Massif. And that response, that's been well responded to by the scientific community. There's no real evidence that we have material coming from Tycho. And so that sort of resolves a new question. If Tycho isn't 100 million years old, then how old is it? For 45 years, we thought we knew the age of Tycho, and now we don't. Lastly, I want to talk about this weird unit called the Sculptured Hills. This is on the east side of the Apollo 17 landing site. Again, we're looking out of the LRO spacecraft window, as it were. And we can see that there's this other unit of material. Here's the Apollo 17 landing site right in the middle of the valley. They went to one spot, basically at the foot of the Sculptured Hills, to sample it late in the mission. Now, this is where we bring in some other data sets as well to help our interpretation. This was, again, the furthest or the last of the EVAs. And at Station 8, you can hear the astronauts' voices. They're getting tired. They've been on the moon for 2 days, working in a pressurized spacesuit. They're working very hard. And so instead of me trying to describe what's going on, I'm going to let Jack describe what he saw at Station 8. What you're going to see or hear is a geologist doing geology, a trained geologist doing his craft on the planet. He's going to describe what he sees. He's going to recognize something unusual, and unusual for a NASA mission. He's going to tell his commander to do something while he goes off and explores the mountain.
Our fender's beginning to fade, and the clip came off on the inside. That's what's wrong. We'll have to fix that before we start. The outside one's holding, but the inside one's not. Bob, all the blocks bigger than 20 centimeters that I've looked at up here are subfloor gabbro in appearance.
Copy that.
I've looked at about 5.
Did we get a mark there on the gravimeter thing?
30 seconds to go, Bob.
Roger, I copied it. Just wanted to check.
Okay, Jack, you find anything up there? G, I'm going to go up and look at this one rock. Why don't you set up and sample any one of these other big ones? They all the same. Like the one near the rover. And I'll go up and try to get this big one down there. Well, okay. It's the only one left to look at, but right now we're dealing with subfloor material, I think. What about some of these little fragments that seem to be sitting more on the surface? Yeah, we're supposed to rake here. We'll get those with a rake. That one up there, by the way, is sitting on the surface. These others are submerged. That's why I want to look at it. If you...
So with the camera on the rover, you can see that there's Gene Cernan, who has been told what to do by his lunar module pilot, which was not unusual for Apollo 17, but would have been highly unusual anywhere else. And there's Jack running off into the distance uphill to go sample that one rock that looked different. And as a geologist, again, it was out of context. That sample didn't look like everything else. And so he thought, well, if I'm going to sample anything, I'm going to go get that one rock. And so he went up the mountain, the hill, started sampling at it, because he knew that it was a big rock and he was tired. He tried to kick it down the hill, which was hard to do. So there's several seconds of him trying to kick at the rock to roll it downhill. I won't show much more of this, but this is from a website created by a buddy of mine, Ben Feist. It's called apollo17.org. And when everybody goes home, clear the calendar for a couple hours, and you'll get to watch either the video, the photos, and hear and read the words that the astronauts spoke over the course of their entire mission, the 12 days from launch to splashdown. It's very well worth putting this mission into the full-time context that we have. But what you saw there was Jack describing what he was seeing, recognizing that there was nothing unusual except for that one boulder. So he went and sampled that boulder, and it turns out that one rock was very unusual. Unlike other boulders sampled at previous stations, which are shown here, those large boulders had trails. And we can, with these images, find where they came from on the side of the mountains. And the reason we do that is, again, context, knowing that the sample they collected at the bottom of the hill came from halfway up the mountain. They didn't have to go up the mountain. The rocks came to them. However, at Station 8, they found that small boulder. It had no boulder trail. It had no context. But it had a very unusual composition. And so using data from another mission, the Chandrayaan-1 mission, an instrument, the Moon Mineralogy Mapper, which mapped the composition of the surface. And so this color map shows variations in composition. And the different colors represent different compositions, from volcanic being the high iron volcanic rocks in yellow to pyroxenes and olivines in turquoise and red. And so the composition of that boulder, that unusual boulder that Jack sampled, essentially matches the composition from those pixels right there. And so using the spacecraft data, we can tie the history of that rock back to being from the sculptured hills. And so in Apollo 17, when they recognized that, we don't think we sampled anything from the sculptured hills 45 years ago. Indeed, today we know they did. And now we can use our understanding of that one sample, the age of that sample, the depth at which that sample came from, to better understand the history of that very odd unit, the sculptured hills. And it turns out that that material may have been ejected by an impact basin 1,000 kilometers away, which deposited at the Apollo 17 landing site. And so putting that sample into the context of multiple data sets now gives that rock new life. So just to summarize, in the last 2 years, we've rewritten a portion of the lunar textbook, where we once thought that Tycho was the cause, the trigger of that beautiful avalanche. It now appears that, indeed, a local event, namely the tectonic moonquakes caused by the Lee-Lincoln Scarp triggered avalanches, that the sculptured hills were indeed sampled, and that boulder comes from a complicated history, perhaps from a spot thousands of kilometers from the Apollo 17 landing sites. We've also found the sources of these boulders that were sampled, putting them into this context. It's like real estate, location, location, location. Geology is context, context, context. But our exploration of the moon is ongoing, and it's not just of Apollo 17. It's of future landing sites, of places that we may never visit, but are still geologically interesting. And so as I begin to wind down here, I want to just leave people with a few thoughts. Next Saturday, October 28th, is International Observe the Moon Night. Tonight you're going to have a chance to observe not the moon, but in a week you'll have a chance to observe the moon. And so we would encourage people to get outside, find a local event or start your own event, and go to observethemoonnight.org. Follow the mission that I participate in, the LRO mission, on Twitter, if you're on Twitter. But also seek out a music video that we put together called The Moon and More, part of which was filmed right here. We just learned this week that we'll be under consideration for a Grammy, which for a NASA mission is a first. I'd love to see the Mars rovers do that. And so the moon is exciting, and it's still new after almost 50 years of exploration. We have a lot to learn from the moon and of the moon, from the past missions, from Apollo, from present missions such as LRO. And we do that not just to prepare for future missions, but also to better understand the moon in the context of the Earth and our entire solar system. The Apollo program has left a legacy that we are still unraveling, not just the legacy of the samples, but of the people. There are Apollo engineers, astronauts, scientists who are still around and telling stories. Their stories are worth hearing, worth understanding, and worth seeking out. And then lastly, and perhaps most importantly, the solar system is an amazing, amazing place. Everybody in the solar system tells us something important about our very, very special corner of the universe. The moon is unique because it gives us an opportunity to put all of those other bodies into context of the processes that shape the planets. Not just the planets in our solar system, but other solar systems as well. And so when we look at the moon, we're looking at reflected light from the sun, and on a new moon, sometimes you're seeing reflected light from the Earth. And so the moon reflects on us our processes and what's happening all across the solar system. So when we want to look at the moon, sometimes we're looking back at Earth. With that, I'll thank you and take some time for questions.
Okay, so I have a microphone.
So I think some of your work currently is on the far side of the moon. You've talked mostly about the near side.
Yep.
What can we learn from the far side, and what can that tell us about those?
So one of the most important things that we have to learn about the far side, well, I think there's two big things to learn. First, I talked about what it means to be a geologist in context quite a bit. Understanding the age of this basin, the South Pole Aitken Basin, which is the largest feature on the moon, and we don't know how old it is. We don't know if it's 4 billion years old or 4.4 billion years old. And as a geologist, again, it's that storytelling. We want to put the chapters in order. And right now, we don't know where that chapter, that part of lunar history, which is a big event. This is a global scale event. Material from that one event will be widespread across the moon. But we want to understand its age and what's exposed at the surface in the interior of this basin. So by sampling that basin, returning those samples to the Earth, we can learn its age, what's exposed there, where it came from. When we know that age, we know about when objects the size of that were striking the moon, and by association, the Earth. For every one crater we see on the moon, there are 3 that would have formed on the Earth. Now, most of those craters on the Earth are long gone. And fortunately, a crater that size isn't around on the Earth, because if there was a crater that size on the Earth, it would have been formed sometime in the last couple 100 million years, and we would not want to see that. And so that's one question. The other is why the far side and near side are so different. One of the things we've learned over the last several years is that the far side, the crust, is thicker. It's about 60 kilometers thick on the far side versus 40 to 20 kilometers thick on the near side. We don't know why that is. Part of it could be some process that happened at its formation, and so we really don't know if there are compositional differences on the far side versus the near side. So a sample from further north on the far side would be really, really useful. Another useful thing would be understanding the structure of the moon on the far side. At several of the Apollo landing sites, we landed seismometers. These seismometers were left in those experiment packages and operated for several years. Actually, on September 31st, we marked the 40th anniversary of the termination of that experiment. Those were left running for several years after Apollo, but were terminated prematurely to save money. Not one of NASA's finest hours. But as we see, all of those seismometers were on the near side. So having a seismic network on the far side might tell us something about the structure of the moon, which would give an indication of how different the far side is from the near side as well. Now, I mean, as a geologist, I can say we'll send 30 landing sites all across the far side and sample everything. That's not realistic. But if we pick 1 or 2 spots that we could potentially get samples from, that would be useful. I should point out that in addition to the 6 Apollo landing sites, there were 3 robotic Soviet landers that landed all along here in the early and mid-1970s. So we have samples from Apollo, from the Lunar sample return missions. We also have meteorites from the moon. Meteorites are wonderful. We know that they come from the moon, but they lack that context of where they came from the moon. So we use those meteorites as kind of this, well, we know they're telling us something, but what is it they're telling us? The moon had to form this rock, but where did it come from? And we just don't have that part.
Hi, thank you. I'm just trying to remember my basic science. So the Earth and the Moon are rotating at the same time, which is why there is a dark side of the moon. And how did that come about? And then if you have time, I'm curious about like what your daily life is like, what you specifically do, and also besides the backpack, like what else your dad did.
Sure. So yeah, the reason we have a near side and a dark side, or a far side really, is that the moon is in synchronous rotation. It takes 29.5 days for the moon to go around the Earth. It also takes 29.5 days for the moon to turn on its axis. So actually, I need a volunteer. Yeah, the bright shirt's the only thing I can see. So come on up here. All right, buddy. So you're going to be the moon. Congratulations. You just got a promotion. All right. So you're going to have to, I want to be the Earth. How long does it take the Earth to go around once?
Well, in full on axis.
Yeah. It's around a pole. 24 hours. Very good. So the Earth does this every 24 hours. Now the moon is going around the Earth, right? So you got to go around me, but also you have to keep your nose pointing towards me, the near side. The man on the moon has to face me. So as you're going around, your name is? Brady. So as Brady's going around me, he's also turning at the same rate at which he's going around me. As I'm spinning around 24 hours a day, he's going around 29 and a half days as it takes him 29 and a half days to go around. Before you get dizzy and fall off the stage, thank you, Brady. So that's a very simple demonstration, but shows that the moon is spinning on its axis very slowly once every 29 and a half days, which is the same amount of time it takes for the moon to go around the Earth, which is why we have roughly one full moon a month, but sometimes we get two and blue moons. I hope that helps. And I can show you some video or point you to some videos of that. Then my dad built two parts of for the Apollo program. In the backpack, he built some of the valves to help the astronauts breathe, which was pretty useful. And if you've ever seen the Apollo 13 movie, which I highly recommend, it's one of the best representations of what a trip to the moon was like, albeit with one major difference. In the famous scene where the carbon monoxide is building up in the command module and lunar module, they have to get a new scrubber. There was the square scrubber and the round scrubber. He built the round scrubber for the lunar module. And so several years ago, my dad was at a book signing with Jim Lovell. He said, you know, Captain Lovell, I helped build the lithium hydroxide canisters for the lunar module. Jim Lovell stood up, shook his hand, and thank you for saving my life. Which to my dad was like, well, you know, you kind of did a lot of that work yourself. Don't thank me. But it was still pretty important. And then you asked about my day. My day's, like a lot of people, is filled with meetings. But when I have time to do science, it's really spent in front of a computer, unfortunately. It's spending time looking at the data, analyzing the data, and looking not just at pictures, but looking at the pictures in the context of slope, topography, composition, trying to merge data sets. Running a spacecraft like LRO is a full-time job almost. And so there's a lot of work and strategizing of how do we keep the spacecraft going with limited resources. So over the years, I've sort of learned more engineering philosophy as much as I've learned geology as well. And so that's one of the more interesting things that I do is working with engineers. Trying to communicate with engineers is very difficult. Going from the science measurement we want to make to, well, what does that mean for the spacecraft? Pointing off axis, looking off to the side, maximizing the return from the spacecraft. So that's a little bit of what I do every day, in addition to meetings and telecons and filling out time cards and things like that.
Hi. You mentioned earlier that the near side has more magma on it and thinner crust and all the volcanic activity. Do you think it's because it was tidally locked that maybe the gravitation of the Earth is pulling on that side, like the liquid is actually being pulled out?
Yeah, so I think, and this is where I start getting, when we get into gravitational forces and orbital dynamics, that gets much further from my area of expertise. But one thing to keep in mind is that at this moment in time, this is the side of the moon that is facing the Earth. If you were to go back 1 billion years, the moon would have been closer and orbiting faster. So the near side of the moon has not always been the near side of the moon. So the fact that we have this different side of the moon with more magma on it is not necessarily the way it's always been. It's the way it is now, but if you were to go back in time or even forward in time, it wouldn't necessarily appear this way. It just so happens that now we have this sort of density difference with more magma on the near side, but again, that's not always been the case. So I don't think that certainly the Earth's effect had much to do with the volcanism and where the volcanism occurred. It's just that perhaps that difference in crustal thickness, a thinner crust on this side of the moon, allowed more magma to rise and erupt on the surface, whereas all of that magma would have frozen beneath the surface on the far side, except for the few places that we see that there is some volcanism. So, I think the Earth has very little to do with what we see presently at the moon. Where is our, okay. Yeah.
All right, so we've got a question from one of our online viewers, a
Sure.
Double Space Academy online viewer from New Orleans. Saeed asks, why does the moon always look so light-colored? Like, why is it so white?
Okay, so the reason that that's a good question. So the reason that the moon is so white, so on a full moon, looks very bright. One of the reasons it's so bright is because the rest of the sky is very dark, first of all. So it looks like you have this bright spotlight. The moon at most is reflecting 10, 15% of the light from the sun. So it's actually quite dark. It just happens to be bright because there's nothing else bright in the sky. But the reason it's so bright is that this white material, this ancient crust of the moon, is made of a mineral, mostly of a mineral called plagioclase. Plagioclase has a lot of aluminum in it. It doesn't have much iron. The iron-rich Mare basalts are dark. Iron is a dark mineral. Aluminum in general and plagioclase as a mineral is very bright. And so that color difference is due to the composition, the mineralogy that we see. Basically, it's the abundance of iron in any material that drives its albedo, how bright or dark it is. And so the fact that the ancient crust has very low iron suggests that it's less dense. That's why it floated to the surface in that magma, ball of magma, the magma ocean, which is why we have a low-density crust, except for areas where we've had volcanism. So hopefully that answers your question, Saeed, but it comes down to the composition that we see there.
How many miles? Oh yeah, how long would it take for the Apollo to get from the Earth to the moon?
That's a great question. It was a 3-day trip. 3 days to get there, a couple days in lunar orbit, or several days in lunar orbit, and then 3 days back, on average. So for Apollo 17, they were there for 12 days, because they spent a day in lunar orbit before landing and a day in lunar orbit before coming back. But it took 3 days to get there, 3 days to get back. Now, some robotic spacecraft, for instance, New Horizons that flew by Pluto, it's a small spacecraft on a very fast rocket. It passed the moon in a couple hours. But it's a small rocket, and it didn't have to stop. Apollo had to stop, so they had to bring food, water, all the equipment. They were heavy. They couldn't go as fast, and so that's why it took about 3 days to go. So it's a long road trip.
This will be our last question.
Okay.
Hi, I'm an earth science teacher, and so Steve Kuki is kind of a huge celebrity in the earth science education world. So as a science teacher, I'm wondering, what is it that he taught you that you really remember, or a lesson that really stood out, or a field trip, or something that really struck you and caused a lot of geology?
It's hard to find one thing. I love Steve. So fortunate to wander into his classroom and to really fall, I won't say victim to him, but like his enthusiasm for earth science was so infectious. It made me want to become a teacher. And I almost became a teacher, but got sidetracked by being a professional scientist. What Steve did for me was take a bunch of us interested students to the Adirondacks. And so what became something we were learning in a book or in a classroom became real. We would learn about differentiation of minerals. Great, you see it in a textbook, you see it in some samples you have, but then we could go to the Adirondacks and actually see it in practice. I think I was just looking for something in education that captured my imagination and that I could apply. And so actually see geology applied in the field, in a place like the Catskills or the Adirondacks, was really for me what made it real and something I wanted to do. And his enthusiasm, it wasn't something he just did from 8 in the morning to 3 in the afternoon. It was his life. I was fortunate enough to go out to Oregon this summer to see the eclipse. And I was running an event for the eclipse where I wanted to have some people to help communicate what was going on. So the first person I thought to bring out was Steve. And so even though he was my teacher over 20 years ago now, he's the first person I thought of to get other people excited about science, because for him science is about engaging with people, not just learn this fact, but see it actually happen. So Steve had an amazing way of explaining things that made it real, as opposed to just, well, okay. We've all had teachers where it might be something really interesting, but you just don't explain it well or you don't make it compelling. And he made earth science compelling. I'm convinced he could make, not to crush on economics compelling. Sorry. He could make anything compelling that he wanted to, but it was the passion for learning, for teaching and learning that made it really something real for me. But I think the bottom line was that he would take us out and show us these examples, and also that he lived it. Instead of showing a slide from a textbook of a volcano, he would show slides from a trip he took to the Cascades. So it was him doing it. It was real. He made earth science real, not just something that was in a textbook. And so for me, that was what said, that's what I want to do. I remember very vividly the very first day of my earth science class in the 9th grade. His colleague, Mike Terlizzi, who was my first earth science teacher, did a demonstration. He had a tank of water, and he had a rock and a piece of wood. And he said, which is going to sink and which is going to float? And everybody said that the wood would float and the rock would sink. And he put it in, and the wood sank and the rock floated. And my mind was blown because it was real. That just happened. It wasn't magic. And maybe it would have been a great French teacher or a great social studies teacher, but it was great earth science teachers. Thank goodness New York State mandates earth science. And I actually, as an aside, I almost got pushed out of taking earth science. I had been given the opportunity to go straight to biology. All of my friends were going to biology, and my guidance counselor in middle school said, no, go on to biology. All your friends are going to be there. And I said, no, I'd like to take earth science. She called my mom, and my mom was told, oh, no, there's a problem. My mom was excited that I had finally gotten into trouble. But it was that I didn't want to take biology, and my guidance counselor said he'll never become a doctor if he doesn't take biology. And I got my PhD in geology, so take that, guidance counselor. But it was one of the greatest choices of my life, because it opened that world of wonder. And as the teachers, and Steve is the example of a wonderful teacher, is getting that excitement and working with any student, whether it's a high performer or a low performer, and finding what they're interested in, getting them excited about it, taking them out, showing them that geology is not something in a textbook, that there's mountains to study and understand, and he was the best. And I still talk to him as much as I can, not as much as maybe I'd like, but he's retired and living on a lake, so he's happy too. And so I just thank you for that question, and we should send our best to Steve. And thank you all for coming. If you have other questions, I think I can take a few minutes offline here before we go and start looking at the skies through telescopes. But thank you very much for coming out, and I appreciate your time.